Good morning, everyone. Thank you for joining us today for the Calculating Energy Costs webinar. My name is Beth, and I'll be hosting today's webinar. I'd like to start with a safety moment this morning. Safety is a core value at PGE, and we want to remind you to be safe around electricity. As you consider installing or retrofitting new equipment, please keep safety in mind. We also want to encourage your family and staff to be prepared with an outage kit, and you can visit our website for more safety information. We also want to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings, which are open to all Northwest utilities and their customers. Before I introduce this morning's presenter, I'd like to show you some tools you'll be using during the webinar. To the right of your screen, you'll see several windows. The participants window at the top, then the chat window, and at the end of the webinar, you'll see a polling window. If you have any questions during the webinar, I'd like to encourage you to submit them to me, the host, through chat, and we'll ask the presenter them at the end of the webinar. Because this will be an informal session today, if you'd like to share an example or you have a question you'd like the presenter to address immediately, please feel free to raise your hand using the raise hand icon, which is at the bottom of the participants window. And at this moment, I'd like to encourage everybody to try pressing that. It's a toggle button. You can press it to raise your hand and press it again to lower your hand. Great, it looks like some people have been trying that, so that's good to see. When you do raise your hand, I will unmute you and ask you to ask your question of the presenter. And now I'd like to show you some additional tools. Directly underneath the Quick Start tab, at the top left corner of your screen, you'll see several annotating tools, an arrow, a marker, and a text tool. The presenter will ask you to use these tools on specific slides during the webinar. And now I'd like to introduce this morning's presenter, John McClane, Training and Education Project Manager with Portland General Electric. John has 42 years of wide-ranging utility experience, including distribution field operations, information systems, corporate planning, budget management, and energy efficiency program management. He holds a BS in Business Administration and an MBA in Organizational Effectiveness. He is a project manager for training and education, and he acts as a subject matter expert and experienced instructor on topics of energy efficiency and renewables. John is also adjunct faculty at Clackamas Community College and at Marylhurst University. And now, without further ado, I'd like to hand the presentation over to John.
Thank you, Beth. Well, welcome everyone. It's a gorgeous day out in Willamette Valley in Oregon. I hope the weather is treating you all well. Today's agenda is all about electricity and getting started with energy management. We're going to talk about what is electricity, how to measure it, a little bit about energy savings, how do you calculate the savings for project analysis, what does a simple project evaluation look like, and at the end, there are lots of very good specialists at your local utility here at PGE and other utilities around the Northwest that are just waiting for phone calls from their customers. For today's webinar, I assume you are a non-technical manager, staff, other interested professional whose organization has a lot of energy-intensive systems. We'll be focusing in on a non-residential workplace, campus, retail, industrial process. Although the concepts would work for residential as well. We also assume you want to learn. This is a service provided by our utility to our customers, and the concepts we'll talk about electricity, but they also apply to natural gas, water, carbon footprint, and others, other resources discussed in other seminars. We only have less than 1 hour. We can't cover all the topics, but we can get you started. And it all starts with measuring electricity. This is a picture I like to remind myself of as things change and change quickly. It seems like the average life of a new cell phone is less than 1 year. But this is something that hasn't changed in many years, and that is the idea of what gets measured gets managed. And of course, with your energy bills and water bills, if you aren't monitoring, if you aren't measuring, you really can't manage. And this hasn't changed. Many of the concepts we'll talk about today have been around a long, long time. Some of you may have seen the Deming cycle or ISO standards, International Standards Organizations, about plan, do, check, act. It is a cycle, and the topics we discuss today are most useful in the planning stage, where in measuring you will establish your current state, a baseline which to measure against. You'll identify what are the key indicators, set some goals, put together a team who can lay out a plan. After that plan has been implemented, you will come back and start looking in the check process, which means monitoring, measuring, reporting. You may even hear the word auditing. And it may come out that the plan is perfect, or maybe you require some corrective actions. So this is the cycle of energy management, and these two cycles really require measuring and doing a little simple math. So let's get started. So what is electricity and how do we measure it? The most common example I see in texts and examples of teaching about electricity is to use a garden hose example. If you run up in the morning and take a shower and suddenly all the neighborhood sprinkler systems go on, you may find that your shower is not as high pressure as you need it to be. You'd like it to be a little stronger. You might have a water pressure issue. In the electric business, we call that a voltage issue. So the amount of force or potential applied to that garden hose, the pounds per square inch, I think it's about 80 pounds per square inch is standard in water systems. For your home use, it'd be 120 volts or 240 volts. Commercial applications would be at 480 volts. So the first dimension of measuring, and that you might be in meetings talking about your systems, volts or voltage might be the issue. Second garden hose example is the amount of electrons flowing, or in the garden hose, the amount of water flowing through that hose. Obviously, if you want to get more water from point A to point B, let's say you have a rainbird sprinkler. Well, rainbird sprinklers won't work on small half-inch hoses. You need a 3/4-inch hose or even a bigger line. If a fire truck pulls up, they've got an even bigger hose. So the amount of electrons flowing in a circuit, that's what electricity is electrons. The bigger the wire, the same as the bigger the hose. The more electrons or the more energy you can flow down that line. In that world, in our world, you would call that the amp. So when you hear amps, it's about the electrons. It's about the size of the wire. You might be hearing about the panel in your building or the panel that's out in your garage in your home. Homes are 200 amps is the common maximum capacity of that panel. Of course, in a commercial or industrial application, that would be a lot larger. So volts and amps are the two main dimensions, pressure and volume. When I multiply one times the other, volts times amp, we get the mighty watt. And this is should be the beginning of recognizing the energy on your bill is all about watts. It is the amount of power. You can have high volts and low amps. You can have high amps and low volts, but the watt is what power is all about. Single phase, you may hear that term. All of residential and most commercial are single phase. If you get to larger commercial industrial, you might hear the word three-phase. So I'm going to give you some of the formulas you might hear about, but we won't cover today. In that case, volts times amps times the square root of 3, which is a 1.7 constant, times something called a power factor. Some of our very largest industrial customers might have a power factor problem. You may see that on your bill as kVARs or some other terms. Again, we won't cover that in today's course. The other term you might hear is the mighty ohm. Something called Ohm's law is where all this comes from. And I've never heard a customer pay for an ohm or see an ohm on their bill, but if they talk about controls or electronics, you may hear the term ohm. That's the resistance to the flow of those electrons in that wire. So we're going to concentrate on volts, amps, and watts and use single phase for all of our examples today to keep it very, very simple. So on your bill, about 90% plus or minus a little bit of your bill is all based on a price times a kWh. There's also a kW, a demand charge. We won't talk about that today. But most of your bill will be a price times a kWh. Now, this acronym is interesting. When I've seen customers in focus groups, they're not quite sure what that is. They know what a gallon of gas costs, they know what a quart of milk costs, a pound of meat, but they aren't quite sure about the kWh. And one of the reasons is this acronym stands for three things, not one. If I tell you Trailblazers in Portland and they belong to the NBA, that's the National Basketball Association, a three-letter acronym standing for one organization. kWh is really split into three things laminated together. So let's break that apart. The first part might be the K, and the K is back to the magic wonderful classes that we've all taken on the metric system. The K, the M, the G, if you Google it, there's a whole list of metric terms out there. My personal favorite is the yottawatt. The magic Y stands for 10 to the 26th, 10 to the 24th, a lot of zeros. So the first part of this acronym could be a K. If you read in the newspapers about a power plant, it might be an MW, not a KW. So it can be a little confusing, but it's all about the number of zeros. It turns out when you buy a piece of equipment, it's measured in W's, a 100-watt light bulb, for example. But when you go to pay your bill, you pay by the kW, not the W. So you immediately have to convert by dividing by 1,000. We'll talk about that a little later. The middle part of the acronym is the W, but it could be a V, and it could be an A, or a whole series of other things like the O for ohms. So you could have a KW or a KV or KA. So the middle part is very flexible. On your bill, it's all about the W. But if you're looking outside and you see the power poles with the wires on top, those would be described as 12.5 kV, 12,500 volts. Third part of the acronym is the dimension of time. Once you have a certain amount of watts and you have 1,000 of them, you rent watts by the hour is one way to look at this. It's not a gallon of gas or a quart of milk that you can store. When you flip that switch, you're renting kWs by the hour. So H is the most common term. Occasionally, again in the newspapers or if you're in large applications, you may see KWA or AKW. And basically what they've done is divide by the number of hours in a year. 365 days times 24 gets you 8,760 hours a year. You stay long enough in this business of monitoring and measuring electricity, you will know the term 8760. Best example is if you have an office complex and you have a lot of required exit signs and you're budgeting and trying to figure out how much energy is used, you know that they have to be on 24 hours a day, 7 days a week. So you would budget 8,760 hours a year times the wattage of all those exit signs would give you the amount of energy times the price for your budgeting purposes. So 8760 is a really useful number. If you ask your staff what's going on and they say, well, it's on about half the time, it would be half of 8760. So that's a pretty useful number. Three-part acronym, KWH. About 90% of your bill is going to be kWh times a price. So let's get into the formula. Basic formula is find the watts. By federal code, if you buy equipment, it is going to have a label that tells you the wattage. If you divide that by 1,000, you get to kW. If you then multiply times the number of hours that equipment is on, you will get to kWh. So watts divided by 1,000 times hours gets you kWh. Here's a quick example, 20 light bulbs at 100 watts each. Hopefully nobody has this actually going on. We've all converted to CFLs or LEDs, but if you still have incandescent bulbs, that would be 2,000 watts, and divide by 1,000 for each hour that they are on, you're using 2 kWh. I've actually had a manager come to me after one of our classroom seminars and tell me that he has put this number, the per hour wattage use, next to the switches of all the equipment in their shop so that people know for every hour you leave the switch on, you're using that amount of energy. And he found it was a very effective way to get people to pay attention to making sure that something wasn't on that shouldn't be. So here's where we get to use our symbols up on the left-hand side of your screen. I'm going to select on the arrow symbol and show you that I can put that arrow anywhere on the screen. So I want you all to pick the answer here. How many kilowatt hours are used by this 60-watt light bulb if it is on 10 hours a day for the next 30 days? So this is a simple example of trying to calculate how much energy is a particular piece of equipment using in my monthly bill. While you're wrestling with that, I'll tell you a story of one customer that I talked to and visited with. They were a used car sales lot. And around the lot at night on this street, he had about 1,000 incandescent bright bulbs to kind of glare and shine off the cars, kind of show off the product. And it turned out that this little sample here would be very cost beneficial for him to switch out the lighting. He couldn't believe that he was spending over $800 a month just lighting around the parking lot, and he could significantly reduce that bill. So it looks like people have taken a good guesses. We've got a good smattering of examples. Here's my answer. If you take the 60 watts using the formula I gave you, you divide by 1,000, you have 10 bulbs that are on, or 10 hours a day for 30 days would give you 300 hours. You do that math, you're going to get 18 kilowatt hours per bulb. Again, if you're this customer with 1,000 bulbs, that would be 18,000 kilowatt hours. So let's see what would happen if I change. Let's see if I can use the eraser real quick. If I change this to a compact fluorescent bulb, and instead of 60 watts, there we go. Instead of 60 watts, we have 18-watt light bulb. What now might be the answer? So redo the math and show me what you think might happen here. If this customer replaces all these bulbs, how much savings they might get. And it looks like Laura already has an answer. Here's my answer. 18 watts divided by 1,000 times the 300 hours would be 5.4 kilowatt hours. So suddenly we dropped from 18 down to 5, a significant cut in the electric bill, especially for the car lot with surrounded by incandescent lights, all lit up like Christmas time. Significant changes, and this is why lighting is probably the #1 place to look for energy savings. But to get the money to make that change, you have to calculate how much energy am I going to save. So I like to find these formulas useful everywhere. And my good example here is, we play the game Jeopardy, 1,210,000,000 watts is the answer. And this was a case years ago. I was in the movie house and found, my gosh, they actually are using the math. So see if you can guess what the movie is I'm thinking about. Here's my first hint. Happens to be an electric vehicle. Here's my second hint, and this, of course, is the infamous flux capacitor. And, of course, the issue in Back to the Future movie was Doc Brown trying to figure out where in the heck am I going to get 1.21 gigawatts. When I was in this movie, I elbowed my wife and said, ooh, ooh, and she said, be quiet. Because this math is relatively accurate, that lightning was the only place they were going to find that kind of power when they went back in time. It turns out if you read the label on this electric time machine, it would say 1.21 gigawatts is what this is required per trip. So if you were the energy manager here and said, I wonder what that costs, how many kilowatt hours does it take to charge this vehicle? Remember, lightning only was there for 1 second. You could now do the math. We have 1,210,000,000 watts divided by 1,000 times the number of hours. In this case, 1 second is 1/3600th of an hour. Therefore, it's 336 kilowatt hours per trip. If you're paying on an average, U.S. average of 10 cents a kilowatt hour, it would cost you about $33.60 per trip. Very economical, even in the movies, to have electric vehicles. So the math works on a lot of different places. You might be in meetings and hear the terms, other terms that can be converted to watts, but the discussion is around tons of air conditioning or refrigeration or horsepower. If you have tons, we need to introduce another term for efficiency. I've had customers come to me and go, "Oh boy, purchasing manager was really happy. They bought a 5-ton air conditioner and was extremely happy with the purchase price, and that's fine for the purchasing manager, but they forgot to check the efficiency rating." In this case, EER stands for Energy Efficiency Rating, or SEER would be Seasonal Energy Efficiency Rating, and there are other terms. You may have to ask your contractor or facility staff or even call the utility. But in this case, we have a 5-ton air conditioner, and its energy efficiency rating is 10. And if you run this little formula, you'll find that it can be converted to 6,000 watts. If you buy another 5-ton unit, it may cost you a little more, but at 14 EER, it only uses 4,286 watts. So the purchasing manager is happy that he got a great deal, but the facilities manager may be very unhappy that you just locked in 15 years of energy bills for this unit that are 40% higher than they needed to be if you had spent a little more money to get the more efficient unit. So this is kind of the classic first example that we run into. I've talked to school districts and some of the governmental institutions to where even in businesses where the budget for capital is controlled through a different decision process than the budget for operating and maintenance costs, where the energy bills are usually contained. So you've got a split decision making between the capital cost and the operating costs. And quite often you'll see they'll go for the cheaper first cost unit even though it locks in higher energy prices. So read the labels is my first advice, and understand how the formulas, simple formulas, work for energy. Horsepower, this is an example of the same thing. I've talked to one customer, and many of our business customers have operations that go outside of the normal 8 to 5 Monday through Friday range. It may be motors for all kinds of operations that can't be down. And so if something breaks on a weekend or the middle of the night, they're running out and purchasing wherever they can a 5 horsepower motor to be replaced very quickly. Again, if they pick one that's 88% efficient, you use 4,239 watts. If they pick one that's more efficient, 4,054 watts. Again, the purchase decision can quite often lock in higher or lower watts, and therefore energy bills for the next 10 to 15 years for that piece of equipment. Again, I had a great customer suggestion that on his equipment, he actually put on the equipment little tags that said, if this breaks, here's the specifications I want in replacing it, so that he got a higher efficiency rating than he might otherwise would have gotten. I thought that was a great idea, labeling the equipment. So another example given to me by a customer was the idea of amps. We've gotten watts, and when you purchase equipment, check the watts, checks the efficiency. But quite often when you're putting in a new piece of equipment, it requires installation, and there's another choice here. Here's 2 60 horsepower motors, both rated at 48,000 watts, so they have the same efficiency. But one motor takes 480 volts and the other motor takes 240 volts. So the math would be volts times amps equals watts. So the 480 volt system times 100 amps gets you 48,000 watts. In the second case, the 60 horsepower motor has 240 volts times 200 amps to get to the 48,000 watts. You would think on the electric bill, those are the same, and they are. However, remember we talked about the volume and the garden hose size. More amps means bigger wire size. If that's copper, you just doubled or more than doubled the cost of the materials to install this piece of equipment. If that piece of equipment is on the other side of the building from the service to the electric company, you might have a pretty long run here of copper. Also, line losses are a function of amps, so you could even have a voltage issue the further away you get from the panel. The answer then would be, gee, I might want to spend a little money on the 480 volt motor rather than 200 volt motor because of the installation costs, not because of the monthly bill. In some cases, I've heard that, gee, to put that extra equipment out there, the panel in this building has a limit. Remember I said 200 amps is a residential, it might be 1,000 amps for a commercial application. And if this equipment says, oh, I have to go past 1,000, you'd have to replace the whole panel to get larger capacity. Changing the voltage of the equipment can reduce the amps. So this is a nice little chart to remind you of that. Watch out for purchasing. Check not only the watts and the efficiency, but the voltage can often be another way to reduce your energy costs at installation. So here's my little cheat sheet. A lot of these slides I've produced so that you can print them off, pin them on a board somewhere, or keep them in a folder, keep them handy for keeping track of discussions. Some people like the step 1 through 4, the procedural approach, and other people like the algebra. I've given you both here. Find the W. That could come from looking at a label, or you might have to take volts times amps, but usually it's the label. Then divide by 1,000 to get to kilowatts. The number of hours of use is probably the most mysterious and unmonitored number to get to energy costs. People really don't have a good understanding. There are things called data loggers. There are ways of getting at this. Ask an expert, call your local utility. They might have, in some cases, support for that, or the Energy Trust of Oregon. So lots of ways to get at the hours, but it may require a little extra work. Once you have the K, the WH, then the final step is multiply it times the price to get the energy cost. Or watts divided by 1,000 times hours times price for the algebra majors. So let's look at another example. Again, pick up your arrow at the upper left-hand corner of your screen and help me find the answer to this question. At an office area, we have 40 fixtures. Each one uses 90 watts. They're on 10 hours a day, 7 days a week. 8 cents is the price, and assume a 30 days in a month. While you're doing some of that math, I would tell you that this is a lot. Being an energy manager or doing this kind of monitoring really is, the world is a word problem. It's not going to be handed to you. You may have to go figure it out. I feel like it's like the TV series CSI. You're a energy crime scene investigator trying to figure out what is happening, what costs do I have to run things, why are my bills low, why are they high. So this is quite common. The first step is to have somebody go out and figure it out, look at labels, estimate, or even monitor how many hours are involved. It may not be as simple as just asking a question. You may have to actually spend some time to collect the data. In this case, we have someone marking an X for 46 bucks, another one at 86 bucks. Here's my answer. The wattage is 40 fixtures at 90. You divide by 1,000 times the 300 hours, 10 hours a day, 30 days, times the 8 cents. I get $86.40. So let's look at another example. This one I'll do for you. A customer has choice between 2 air conditioning units. This is getting back to that purchasing decision is often where you can really lock in future bill savings. I'm going to assume 10 cents simply because it's easy to do the math in my head. And the common evaluation is, oh, this more efficient unit that only uses 1,000 watts costs me more money. This is very common. So the question, if you want to go get money to do this, the CFO or the budget manager are going to say, how many years will it take me to get my $100 back? This is the infamous payback period and is the most common way to evaluate. So let's take a look at this. Find the W. Well, the difference between these two machines is 1200 watts minus 1000. I have a 200 watts in savings. If I divide by 1000, I would get 0.2 kW. Here comes the hours of operation. We estimate you only have air conditioning 4 months a year, 30 days in a month, and about 6 hours a day. You'd have 720 hours of use on this piece of equipment. If I now take kW times the H times the price, I get $14.40 saved per year. So to answer the question, how long does it take? What's the payback period of my $100? The answer is $100 out, $14.40 a year savings. It takes 6.9 years before I get my money back. My research and questioning budget managers of our businesses, 3 to 5 years is the most common range of payback periods in a budgeting cycle or a capital cycle. In our case, if it's not less than 5 years, don't even fill out the paperwork to make the request. So this project may not be immediately one that you would get approval for, but I would keep it on a list and keep it alive and coming and check back every once in a while. Because in this case, what happens is if you get a $50 rebate from the Energy Trust or the local Department of Energy or a federal rebate, suddenly this number changes quite dramatically. So now my outlay is $100 minus 50 divided by the 1440. I now have 3.5 years payback period. This is now within the range of getting decisions to go to no to a yes. So when you do project examples like this example, no doesn't mean never. No may mean not now. You may want to come back to this project and look at changes. It may be that the equipment gets cheaper, or electric prices get higher, or that rebates suddenly appear. So don't abandon a project just because you get a no just once. Keep coming back to it. Another good example, this was an example I saw in the store, in a retail store where I was shopping, and I saw 2 bulbs, compact fluorescents, and this is another example of read the label. So use your little arrow in the upper left-hand corner and take your best shot at this question. Here are 2 bulbs on the shelf. Your job is to purchase 100 bulbs for your little business. One bulb is $4, another bulb is $5. They are the same wattage. One bulb, when you read the label, says 8,000 hours of life, and the other bulb says 12,000, but costs $1 more. You are asked to purchase. Which CFL would you purchase? This is a great example of looking at another dimension of read the label or getting a hold of your purchasing manager. The purchasing manager say, well, look what a great deal I got, $4 a bulb. But again, if you get a lot longer hours of life, the decision can be quite different. I can see some people are going, hey, I'd buy the $5 bulb, but you've got to justify that. So let's look to see how you would justify that extra dollar per bulb. In my math, I would there's a couple different ways. Buy a bulb at $4 at 8,000 life. It turns out that 10 hours a day for 365 days a year, you would be using this bulb 3,650 hours a year. If it lasts 8,000 hours, in other words, this bulb is going to be there on an average 2.2 years. If you buy the other bulb, it's going to last for 3.3 years because it has a longer life. So you get an extra 1.1 years of lighting before you have to repurchase a bundle of lights. In this case, over 6.6 years, you would have had to purchase bulb A 3 times at $400 versus bulb B, you'd only have to buy twice. So you would save $200. So that's one way to look at it, is you're purchasing costs over time are going to be less. I had one customer remind me that for commercial businesses in this state, you have to recycle compact fluorescents, and they charge you for recycling these products. Well, you just postponed the recycling costs by another year, and that was another cost that they could have put into this analysis of why should you buy the more expensive bulb. So let's talk a little bit about looking at data. When in my youth, when I was doing budgets and forecasting and ran into the boss or the chief financial officer, said, look, and I had this great spreadsheet with lots of columns and lots of rows, and said, can't you see? And the boss said, no, I can't see. It's just a bunch of rows and numbers. It was very difficult to communicate, look what's going on. Once graphing became available, then you could take the columns and rows and data that you've collected to monitor energy and put them in a graph and very simply communicate what's going on or show a change that was either predicted or not. In this case, I've got 4 rows. This is just a monthly bill, 4 years of monthly bills graphed on a chart. In the Northwest here, we're a winter peaker, so I put the winter in the middle of the chart instead of a January through December because we're winter peaking. Most customers have a peak in the winter months. And I charted 4 years, and you can see here that there are 2 winters at the top that are very high use and 2 winters down here that are very low. And sure enough, between these winters, 2 high and 2 low, there was a change, in this case, of heat pump technology, purchasing a very high efficiency. So they were paying attention to the efficiency in their replacement and lowered their winter bills by 40% on average over these 2 winters. So here's a case to where if you were in a business and you went to a budget manager and said, I need some money to make a change, here's a way that you could graphically very quickly show, look, it really did drop dramatically, and that was a prediction. Once you show this chart, you're more likely to get your next project approved if you can produce this kind of monitoring and measuring. In other words, graphs can allow non-technical people to say what changed and why, is my message on this chart. For those of you that have EMS, energy management systems, or have a utility that's giving you hourly information on digital meters instead of mechanical meters, you can ask these questions on an hourly basis, not just monthly basis. In this case, we put, this is a 24-hour clock on the bottom from midnight to midnight, so noon is in the middle. And then the kW use per hour is on the left-hand side. There are many systems that can give you this kind of charts. And you can suddenly, when I first saw this, I thought, oh my gosh, that's a lot of information. That is 30 days mapped one on top of each other. But then it was very easy to start explaining to me what was going on. This happened to be a school. And so you can see up here at the top, Mondays through Fridays all mapped. People start out in the morning, and by 8 o'clock, everybody's there. And starting around at 3 o'clock, people start leaving, and there's this slow drop-off back to midnight. But Sundays were down here, 4 Sundays, and then 4 Saturdays. So this chart made a lot of sense once, a very simple explanation here. Monday through Friday, Sundays, and Saturdays. And it turns out you can ask some pretty smart questions from looking at the chart. If you saw a spreadsheet with all this information on it, it would be overwhelming. So one of the first questions I like was what comes on in 1 a.m. every night, weekdays, weekends, every single night. And I was told by the facilities manager that he kept asking staff, and no one seemed to know what comes bump in the night. It comes on about 1 a.m. and stays on until everybody comes in. And finally, one day, the IT department raised their hand and said, that's the computer backups that run at night. Everybody's computer gets backed up. And the boss said, well, how long does that take? And they said, well, it takes about 45 minutes. And the question was, well, why doesn't it then turn them off? And they said, well, we bought this really good deal on software. It knows how to turn them on. It doesn't know how to turn them off. So the facilities manager recommended that he would pay for the extras special software that not only could turn the equipment on, but turn it off. So he changed the shape from this bump in the night to dropping it down here, back down, and saved all this energy by turning the software off. So that was a graphic way to, number one, identify the problem, and two, go back to management and say, see, the shape did change, and you can show that change very quickly, even in the next month's chart of your 30 days. Another question was, why so long to drop off? If school kids don't hang around all the time, what's going on here that you still have a pretty high energy use in this ring out here? And it turned out it had to do with janitorial service. The janitorial service came in, and their method for keeping track of what was clean and what wasn't in all the classrooms was they turn all the lights on, and when they leave a room, they turn the lights off, which would get you this kind of shape. So they renegotiated with the janitorial service to say, look, turn them all off and come up with some other kind of system to monitor it so that you only have the lights on in the room that you're cleaning. Well, that changed the shape to look like this, and so they saved, all this energy got saved, and that was a big budget. And again, the graph could show you very quickly what you're trying to accomplish. So asking great questions and monitoring the change when you've made changes like this are really interesting. The last one was Sundays. This was interesting that they couldn't figure out why Sundays were higher than Saturday. I mean, some people come in on Saturdays, but not many people come in on Sundays. Well, sure enough, the school district was raising money and were renting Sundays out to a church group to use the gymnasium and other facilities. So now you have a way to measure and say, gee, what are we charging them? Because this shape, the difference between this shape and this shape, that energy right in there, you'd better make sure that you're charging enough to pay for that. And so you can use charts like this to say, well, that is why Sundays are higher, and I've got the math to show that we're charging more than enough to cover our costs of having them use that facility on Sunday. So hopefully these three questions can show you the value of not just tracking and monitoring in a spreadsheet form, but graphing your information can allow you to communicate to non-technical people in a very effective way. So starting to get towards the end here, changes in behavior are areas of focus that I would recommend to people to get started. Conservation means don't waste it. Turn off equipment when it's not being used. Check the efficiency. Change the process. We talked about the janitorial service, but it could be an industrial process. It could be all kinds of processes in your business. And finally, get a hold of that purchasing manager and make sure that when you replace equipment, that the efficiency of the equipment has a proper place in the decision making, as well as the life of the equipment, as we saw with the light bulbs. So that I would always divide my initiatives into these three: behavior change, process change, equipment change. So what are the next steps? I would establish some kind of a feedback process. Start measuring and monitoring. Develop that baseline. There are baselines that are for certain industry standards or business segments. What is the average use per square foot in an office building? What is the average use for a restaurant? There are standards out there. You'll see some names at the end of this presentation you can call and get a hold of that. Develop a list of projects. We talked about the project that initially might have been a no, but could be a yes. So don't get rid of project information. Keep it alive. Stay abreast. Keep checking technology, energy prices, rebates. Keep coming back to that list every 6 months. Have somebody peruse through the Energy Trust website or your local utility website to find incentives that may come or go. Put somebody on this to stay and bring it to you every 6 months or so. So I'm going to end my portion of the webinar today with, if you're a commercial customer at our particular utility, you can contact Paula. If you're an industrial customer, call John Maloney, and I'll turn it back to Beth for any questions.
Thank you, John. I want to remind everyone of some upcoming webinars we have. Up on the screen here, you'll see next week we have CFO's perspective of energy efficiency and renewables, followed by several other topics. And you can find out more on our energyeducationcenter.com website. Before we proceed to the question and answer portion of the webinar, I'd like to remind everyone that you can continue to submit questions to me through chat, and I'll ask them of John. I'd also like to draw your attention to a feedback survey here that I'm just about to open at the bottom right-hand side of your screen. If you could take a few moments to fill that out, we'd really appreciate it. We do value your feedback and use it to improve future webinars. And within a few days, we'll send you a follow-up email of the recording session and a PDF of the training materials. And now I would like to ask John our first question. John, where do you find the energy efficiency ratings or seasonal energy efficiency ratings that you were speaking about if it's not labeled on the equipment? Is there some resource for that?
I would call the two people that were listed on the slide. You can also ask a vendor. There are databases out there where people can look it up. I can remember one case where it was an older piece of equipment, and the customer couldn't read the equipment label, but one of the vendors walked in and said, "Oh, that's a Biltmore. I haven't seen one of those," but they can look it up and they can find it. But it usually takes an expert. It's not readily available. And this is where you get a good relationship with your vendors as well as your local utilities. They can find it. So that's, I guess, my best answer.
Great, thanks, John. This is probably a follow-on question to that. Are there resources or websites where you can find what the best rated equipment are, so the most efficient, what they should improve their equipment to?
The first place I would start is the local utility, or in our case, the Energy Trust of Oregon. And sometimes the state energy department might have standards, and sometimes the federal might have standards. What you will find on those websites is a minimum efficiency standard in order to get a rebate. So they'll give you the minimums. Certainly you will find equipment with higher than that, but it gives you a baseline. If you're purchasing equipment less than what's required to get the incentive, then you know you're leaving savings on the table. So I would check the Energy Trust of Oregon for the people here in Oregon. If not on the Energy Trust system, then check their local utilities.
Great. Thanks, John. And let's see, I have one more question here. You mentioned talking to purchase managers about length of use and different ways that they should be considering replacing equipment. Do you have any suggestions for talking to purchase managers? What should I be showing them?
I don't have anything specifically other than the examples I've shown here today are designed to where you could take this to a purchasing manager. I'd love to see the facilities manager and the purchasing manager get in a room, maybe with the people that are on this previous slide, and have that discussion with the purchasing manager. Quite often they are driven by that capital budgeting or cost per unit. So I think this particular set of slides that people will receive today is a great starting point. I've got an example of how the life can make a difference. I've got an example how the efficiency can make a difference on motors and refrigerators. Those are the most common three: refrigeration, motors, and lighting. But once you get that concept through to a purchasing department, then they can start looking at their purchasing standards and perhaps getting some change. It may take 6 months to a year to actually have a project to review the purchasing standards for equipment.
Thanks, John. And I also want to mention that next week we do have the CFO's perspective on energy and efficiency and renewables webinar, which might help you at least think about how to talk to your CFO. And our last question we have today, unless anybody else wants to submit an additional question, is who can help me with the calculations and paperwork to get incentives? So I assume they mean the Energy Trust. I don't have extra time to spend on this.
There are a couple of things you can do. Again, the two people that are on the previous slide are very good at helping through the paperwork. The vendors are often trained with templates and spreadsheets. So again, your local utility is going to have experts. The Energy Trust is going to have experts that can help you through that. and the vendors are often trained with templates to help you through that. So you're not doing it alone, I guess, is my best advice. Pick up the phone and ask for help. If you're industrial, again, John Maloney, or you may already have a key account manager assigned to you. For commercial, Paula, and they know people at the trust. They know vendors. They can help you. So call one of these numbers or email them and see if you can't get some help. You don't have to do it by yourself. There are lots of people ready to answer your questions. I was doing a presentation at some utilities in another state, and the customers in the course were amazed that, you mean there are people waiting for those calls? And the answer is yes. There are people at the utilities and at the Energy Trust that would love to talk to commercial and industrial customers and help them understand exactly what it takes to get a project approved.
Great. Thank you, John. And that was our last question. I want to thank all of you for joining us today. We'll stay online for a little bit in case any of you would like to chat with us and ask any additional questions. But thank you again. We hope to see you at a future webinar.